Okay, students, now that we've covered solution stoichiometry, in which we have used the molarity as a conversion factor in our dimensional analysis setup, we're going to extend that to a stoichiometry problem in a titration. So before we can do that math, I want to just make sure that we understand the terms that we're using. So first of all, a titration is a chemical reaction. We are running a chemical reaction when an amount of one reagent is added slowly, usually in increments, to an amount of another reagent until that reagent has been completely reacted. So we're adding two reagents together, usually as solutions, and we want to add the second reagent to the first reagent until the first reagent is completely reacted. And at this level of chemistry, usually we encounter titrations in acid-base. Neutralization reactions. Remember, that's one of our 6 basic types. And the reason that we run a titration of an acid-base reaction usually is because we don't know how much acid we have in the solution, or we don't know how much base is in solution. So very often we're trying to find the concentration of one of the two reagent solutions. Well, the point at which the second reagent is reacted completely. So for example, if we're trying to react acids and bases by adding a base to an acid, then the point at which all of the acid is reacted away completely, we are said to have added a stoichiometric amount. Also called a stoichiometric equivalent. And all that means that we've just added enough of the first reagent, the base, to completely react away all of the second reagent, the acid. And the reaction has reached its equivalence point. Now, very often it is not possible to see when the equivalence point has been reached. In our acid-base titrations that we've done in the lab, the acid is a colorless solution, the base is a colorless solution, and the product of the acid-base neutralization is water and a colorless salt solution. So we often cannot see the equivalence point when it occurs. There's no precipitate being generated that we can see. It doesn't turn cloudy. It doesn't start fizzing. So the equivalence point may not be visible to us. To help us determine when we have reached the equivalence point, we can add a special chemical called an indicator. And when we add the indicator in the reaction, the indicator usually will change color very close to the equivalence point. In fact, we choose our indicators. There are many types of indicators that we can use, and generally we choose the indicator that we use because it will change color near where we expect the equivalence point to be. So for example, if we expect the equivalence point of an acid-base titration to be at a neutral pH, so pH of 7, then we would choose an indicator that changes color at approximately pH of 7. So when we add an indicator to the reaction, it will change color near the equivalence point. That lets us know that we are at the equivalence point or near it. And when we see the color change occur, that's of the indicator, we call this the endpoint of the titration. That's when we end the titration. We end the titration when the indicator changes color. And notice that the endpoint may not be exactly the equivalence point. So a common indicator for acid-base reactions is phenolphthalein. PHENOL, PHTH, very odd spelling, PHTH, A-L-E-I-N. And it's not pronounced phenolphthalein. That pH in the middle is silent. So it's phenolphthalein. All one word, phenolphthalein. And we choose phenolphthalein as an indicator for many acid-base reactions because phenolphthalein changes color very close to the equivalence point of an acid-base reaction. In fact, just shortly after we have passed the equivalence point. So we've gone higher than pH 7, and then slightly beyond that, phenolphthalein changes color. Phenolphthalein is colorless when it's in acidic solutions, and about the time that it hits a little bit above pH of 7, around pH 8, then it will turn pink. And if you've run one of these titrations before, you know that it turns a very, very bright magenta color. So it turns pink when the solution becomes alkaline. Alkaline meaning basic or pH above 7. So before we move on and actually start to do these stoichiometry problems that I've set up for you, I just want to make sure that we understand the difference between the end point and the equivalence point of a titration. So I'd like for you to pause the video, and while you've paused the video, in your own words, I would like for you to write a one-sentence explanation that explains why we have these two different terms. What is the difference between the end point of a titration and the equivalence point of a titration? So go ahead and pause the video and write out your own sentence right there. Okay, coming back from pausing the video, you can see the sentence that I've written here to explain the difference. Hopefully yours says something similar to this. So what I've said here is an equivalence point is when you have added a stoichiometric amount of both reagents. Whereas an endpoint is when the indicator changes color and tells us to end the titration. And what is a stoichiometric amount? It means that we've added just enough of a second reagent to perfectly react away all of the first reagent and no more. We don't have any excess of either reagent. All right, with that in mind, we've got a couple of titration stoichiometry problems here. So we're going to work through this first one together, and then the second one I'll ask you to do by pausing the video. So let's go ahead and work through this first one. So sample problem A. If 25.0 milliliters of a 0.100 molar sodium hydroxide solution, so there's our base, were titrated against, that's another way of saying were reacted with in a titration, 35.0 milliliters of, and they don't give me the concentration, of sulfuric acid solution. There's our acid. What must have been the concentration of the acid solution used? So let's parse through this word problem and see what they're giving me. They're giving me the volume and the concentration of the base. And they're giving me the volume of the acid and asking me for the concentration. Well, before I start setting up my dimensional analysis, what is the very first thing that I'm going to have to do? Hopefully you're thinking that you're going to need a balanced chemical reaction, right? Because we know we're going to be doing a stoichiometry at some point, which means we know we're going to be doing a mole-to-mole ratio conversion at some point, which means we know that we're going to need a balanced chemical equation. So let's go ahead and balance this. I have this base and this acid, so sodium hydroxide plus sulfuric acid So now I'm going to get water because the hydrogen from the acid is going to pair up with hydroxide from the base. And in acid-base reactions, it's okay for me to write water that way because it will help me to balance it. And then the sodium pairs up with the sulfate. Sodium is a +1 ion. Sulfate is a 2- ion, so I need 2 sulfates to balance it. So those are my products. Now I need to balance the equation. 1 sodium, 2 sodiums. 2 sodiums, 2 sodiums. 2 hydroxides from the base, 1 OH in water from the base, so I need 2. 2 sodiums, 2 sodiums. 2 hydroxides from the base, 2 OHs in water from the base. 2 hydrogen cations in the acid, 2 hydrogens in water that came from the acid. 1 sulfate ion, 1 sulfate ion. So it's balanced. Okay, now I have my balanced chemical equation. So what's next? Well, now I can do my stoichiometry setup, my dimensional analysis. So let's look at this. First of all, we are running a chemical reaction. So I am not going to use the dilution equation. I am not going to use M1V1 equals M2V2 because I know that that equation is only when I'm diluting a solution and not reacting with something else. So I am going to use a dimensional analysis setup to solve for this stoichiometry. So I have to decide where I'm going to start my dimensional analysis and where I want to end up. And that is one of the biggest challenges of titration stoichiometry. So notice something. Normally in a solution stoichiometry, I start with a volume of one of the solutions. But here I'm given a volume of both solutions. And here I'm given a concentration, but I don't know the concentration of this solution, and that's what I'm being asked for. So right here it says what must have been the concentration of the acid solution used. So I'm looking for the concentration of that. I'm going to write that up here. What is the concentration of that? That's what I'm looking for. So there are a couple of different ways that I can approach this, but I'm going to show you the way that I think will make the most sense, and I think it will minimize your errors when you do it. If we are thinking of the molarity of this acid, I'm going to put that right here. Molarity of the H2SO4 solution. That's what I'm looking for. Well, what is molarity? Molarity is the number of moles of this substance divided per liter of solution. So let's rewrite that and say we are looking for the moles of H2SO4 divided by the liters of H2SO4 solution. So if I can find out the numerator and the denominator, then I can resolve that and I will have my molarity, won't I? So remember, we're going back up here. We're being asked for the concentration of the acid solution. Concentration is molarity. Well, instead of writing molarity, I can write the moles over liters, right, for that acid solution. So if I can get the numerator and denominator of that right there, then I can resolve that fraction and then I'll have my answer. So that's going to be my goal. And in fact, what I can do is I can simplify my dimensional analysis. And I'm going to just try to solve for the numerator. So I'm going to set up a dimensional analysis just to solve the numerator. I want to find the moles of sulfuric acid. Once I get that, then I can just plug in the liters, and they've given me the milliliters here, So I can do another calculation, a separate calculation, to convert from milliliters to liters and plug that in down at the bottom. So I'm going to have two little calculations here. One calculation is going to be a dimensional analysis to figure out how many moles of sulfuric acid I have. The other calculation will be a little dimensional analysis to convert between milliliters to liters. And when I have the answers to those two, I'll just plug them in right there, and then I can resolve it for my answer. So part one. This is not a limiting reactant problem. I'm just doing two separate calculations so I can get the information to plug in to that fraction. So part one, I want the moles of H2SO4. And I'm going to start with my other reagent, the quantity of my other reagent. So 25.0 milliliters of NaOH. I'm going to convert from milliliters to liters. Remember, milliliters has to be on the bottom here in order to cancel out. And then my next conversion step, this is liters of NaOH, right? My next conversion step, I need liters of NaOH to moles of NaOH. This is the solution. And then one more conversion step. I haven't left myself a whole lot of space. One more conversion step from moles of the NaOH to moles of the H2SO4. So can you see what I'm doing? I haven't left a whole lot of space here, but I've got one conversion step here that goes from milliliters to liters of the base. Then I'm going to use the molarity of the base to convert from liters of the base to moles of the base. And I'm going to do one more conversion step, and here's the heart of the stoichiometry right here, to convert from moles of the base to moles of the acid. And then that's going to give me moles of the H2SO4. So when I cancel these out, you can see how they cancel them. Milliliters of the base solution cancels out with milliliters of the base solution. Liters of the base solution cancels out with liters of the base solution. Moles of the base solution cancels out with moles of the base solution. Here's the heart of the stoichiometry right here, my mole to mole conversion, and it gives me moles of H2SO4 at the end. So let's go ahead and plug in the numbers here. We know I have 1,000 milliliters to 1 liter. This is a molarity conversion right here, right? Molarity conversion. How many moles per liter? It's moles per 1 liter. The molarity is 0.100 moles per 1 liter, okay? And then I have my mole to mole ratio, which I'm going to get right up here from these coefficients. 2 moles of the base to 1 mole of the acid. 2 moles of the base to 1 mole of the acid. So if I do this math, I get 0.00126. 3 sig figs there, right? So that's how many moles of the acid I'm getting, and that's going to go in the numerator right there. You see how we've done part one to figure out the moles of the acid, so I can plug it in right there? Because I'm trying to find out the molarity, the concentration of the acid. And so I can do that in 2 different steps. All right, so let's do the next part, and I'm going to figure out the liters of the acid. So part 2. Starting with 35.0 milliliters. Of the sulfuric acid. And I want to get to liters, so that's pretty obviously only going to be one step. So I'll have liters of the acid solution when I'm done with it. And let's see, the only conversion step I need here is milliliters of the acid to liters of the acid. 1,000 milliliters to 1 liter. And so my answer here is 0.0350 liters. And that number is going to go right there. So you can see my strategy here for doing this problem. I saw that I had a solution stoichiometry problem because I was reacting a volume of a certain concentration of one solution to a volume of another solution. So I'm running a chemical reaction. So I knew I was going to have to do a stoichiometry problem. So I knew I needed the balanced chemical reaction. In this case, they did not ask me for an amount, a quantity of something like the number of grams or the number of liters or the number of moles of something. They asked me for a concentration. And a concentration is a derived unit. A derived unit has units in the numerator and in the denominator rather than just a single unit. So by asking me for a derived unit, a concentration, I rewrote that as the numerator and the denominator. And then I set out to determine the numbers that I would plug into the numerator and in the denominator. So now I have the numbers that I'm going to plug in here. I can do that. So this is 0.00126, and this is 0.0350. Because molarity is the number of moles of solute per liters of solution. So that's what I've gotten. And now I'll just borrow a little marginal space here to get my answer. I'll do this math. And my answer has to be to 3 significant figures. So even though my calculator only gives me 2 sig figs, I know that I have to add a 0 at the end. So my answer here is 0.0036 is what my calculator says, but I know I need 3 sig figs. So I'm going to add my 3rd sig fig there. And this is the units are molarity units. And there's my answer for this problem. So the way that you get good at doing these problems is just doing practice. You do enough of them so that you can start to recognize the pattern and the methods by which you can solve based on the patterns that you start to recognize. In this case, I saw that I was running a chemical reaction. I recognized that it was a stoichiometry problem. And in this case, they were asking for a concentration rather than the number of milliliters or liters or moles or grams. And so I took concentration and I broke it apart so that I could consider the individual components of what a molarity concentration is. I solved for each of those separately, and then I plugged them back together to get my molarity. And that's how I solved this problem. Okay, well, that's how we do it. And to give you an opportunity to practice here, I've given you another sample problem. So I'd like for you to read through that problem and see if you can solve this titration stoichiometry problem. Go ahead and pause the video now and give it a shot. All right, coming back from pausing the video, we've got this titration problem, sample problem B, and I'm going to work through it with you here. Rather than just showing you the answer all at once, I'm going to take the time to talk my way through it so you can hear my thinking process as we do this. So it says, if 10.00 milliliters of a 0.1050 molar sulfuric acid solution, so they're giving me a volume and a concentration, we're titrated with, which means we're reacted with, a sodium hydroxide solution, so there's my base solution, and 11.45 milliliters of the base solution were required. So they're telling me what the volume is of the base solution. What was the concentration of the base solution? So here again, notice that they're asking for the concentration of the base solution. So they're asking for the molarity of the NaOH solution. Well, I know in order to do all of this, it's a stoichiometry problem. I'm going to need to go through a mole-to-mole ratio at some point, and that means I have to have a balanced chemical reaction. So let's go ahead and redo our balanced chemical reaction. It's the same as the one above. Next, I'm being asked to calculate a molarity of the sodium hydroxide. And instead of trying to figure out what the molarity is, I'm just going to rewrite that to say moles of sodium hydroxide over liters of that sodium hydroxide solution. And once I get those numbers, I can plug them in here, and then I'll get my answer. So I'm going to have part 1 for the numerator and part 2 for the denominator. Part 1, I need to figure out the moles of the sodium hydroxide. So moles, I'm just going to make a little bar there so that I know that this is not part of that calculation. I'm just drawing these lines here. So the goal of this calculation must be to get to the moles of the sodium hydroxide. So I'm going to start with the quantity of my other reagent, which is a 10.00 milliliters of the acid. I could write out H2SO4 aqueous, so I'm just going to refer to it as the acid here. I have my first conversion factor to get from milliliters to liters. Milliliters of the acid to liters of the acid. My next conversion factor is going to be the molarity of the acid to allow me to get from the liters of the acid to the moles of the acid. And then my last conversion factor is going to let me convert from the moles of the acid to moles of the NaOH, right, which is the base. Okay, there's my setup. Let me plug in the numbers. 1,000 milliliters to 1 liter. This is the molarity calculation, right? And this is going to be my heart of the stoichiometry right there. So how many moles per liter for the acid? 0.1050 per liter. That's what molarity means. The mole-to-mole ratio from the acid, it's 1. To the base, it's 2. And if I do that math, remember I need 4 sig figs here, 4 sig figs. So my calculator only gives me 2 sig figs, 0.0021. My calculator only gives me that, but the calculator has thrown away my significant figures, so I know I need 4 of them. So I add 2 more zeros. So there's how many moles of NaOH I have, and so that comes down here. 0.002100. Now for part 2, I'm going to calculate what the denominator should be. So the liters of the base. So I start with the volume of the base in milliliters. And it's going to be a one-step conversion to go from milliliters of the base to liters of the base. And of course I have 1,000 milliliters to 1 liter. And that's going to give me an answer of 0.01145 liters of the sodium hydroxide. So I know what goes down here in my denominator. Okay. So again, the way that I approached this problem is I saw that they were asking for a concentration. I also recognized that this was not a dilution problem, so I was not going to use M1V1 equals M2V2 because that would have given me the wrong answer. Instead, I knew this was going to be a stoichiometry problem because I'm running a chemical reaction. So I needed a balanced chemical equation, and since they are asking me for the concentration of a solution, they're asking me for a derived unit. Remember, a derived unit, like molarity, is a unit that has something in the numerator and something in the denominator. So for a derived unit, I can treat it as two separate problems. I can break it apart and figure out what needs to go in the numerator and figure out what needs to go in the denominator, and that's how I did this. I broke this into two separate problems to figure out those numbers, and now that I've got those numbers, I can do the math, and my answer needs to be in 4 sig figs, so my answer is 0.1834. And the units of measurement are moles per liter or capital M for molarity. So there's my answer, 0.1834 molar solution for the sodium hydroxide.